Suppose we roll a die over and over again, only stopping when we roll a 6. Sometimes this could take many rolls. Sometimes we may roll a 6 immediately. But how many rolls would it take on average? Well, because a die has 6 sides, and they're all equally likely to come up, and only one of the sides is a 6, we would expect on average to have to roll 6 times to get a 6. But during a lecture at the University of Pennsylvania, mathematician Elchanan Mossel posed a much more interesting question. It's very similar to the question we just discussed. We throw a die until we get a 6, and we're asking what the expected number of throws would be. However, we have this additional condition that all of the throws of the die gave even numbers. Here are the multiple choice answers you can pick from. We may expect that on average it will take 1 throw. We may expect that on average it takes 1.5 throws, or 2 throws, and so on. I encourage you to let me know what you think the correct answer is in the comments. I'm going to show you the poll results for this question, and you'll see that the overwhelming favorite is not the correct answer. We'll see why people usually get this question wrong, and then I'll show you both intuitively and more rigorously what the correct answer is and why. Before we take a look at the poll results though, why don't we try doing a few trials ourselves? So what we're looking for here are sequences of dice throws that end with a 6 and where every other throw was even. Let's see an example. My first throw is a 3, so this would not count. Trying again, I get a 4, so we're okay so far, and then I roll again, and I get a 2. Alright, still even throws. We would stop as soon as we get a 6. Here we get another 2, and then I roll again, and I get a 1. So we had a long sequence going, but because we just rolled an odd number, we would throw this whole thing out. Remember, we have this condition that all the throws have to give even numbers. And the question is, among all sequences like this that end with a 6, what's the average length, the expected number of throws that it takes to get to that 6? So trying again, I roll and get a 4. And then we get another 4, and then a 4, and then rolling my green die, and at last I've got a 6. So this is the type of sequence we're looking for, a sequence of even throws ending with a 6. The length of this one happens to be 4. But how long do you think these sequences are on average? If you said 3, then you agree with most people, and you are wrong. Here are the poll results from Jill Calais' blog called Combinatorics and More, which is where I first saw this problem, link in the description. You can see that nearly 50% of people picked 3 as the answer, and there's a decent spread of answers throughout the rest of the options. It turns out the actual correct answer to this problem is 3 halves. The fact that the correct answer is 3 halves or 1.5 is one of those paradoxes that isn't actually a paradox. It's a true thing, but to a lot of you, even some of you who know probability theory, this probably feels very wrong at a glance. And that's what makes this one of the best math paradoxes I've encountered, that if you know a bit of math, you're perhaps even more confident in getting this answer of 3. Why would you be confident in that answer? Well, intuitively, without much math jargon, knowing that we have this condition that all the throws are even, you would say, okay, the possible rolls then are only 2, 4, and 6. Then, since every side of the die is equally likely to come up, certainly we would expect 1/3 of the rolls to be 6. Then, if 1/3 of the rolls are 6, we would expect on average to have to roll the die about 3 times to get a 6 and end the sequence. This is nearly so obvious, so simple, and so convincing that it seems preposterous to consider the answer is actually half of this. And if you have some mathematical background in probability theory, then you may be even more confident in this correct answer, recognizing this as a geometric distribution with parameter p equal to 1/3. This describes the number of rolls, say n, that it takes us to get a 6 on the condition that all of the rolls are even, and so there are only 3 possibilities. And all the math folk know that the expected value of a geometric variable like this is 1 divided by that parameter p. in this case 1 divided by 1/3, and so the expected number of throws, what we call the expected value here, would be 3. But again, the correct answer is not 3, it is in fact 3/2, or 1.5. So why is that? How could this possibly be the correct answer? To make sense of this problem, it's important that we take an accurate view of our sample space. Now, when we're just repeating throws of a die, we may say that our sample space, the set of possible outcomes, is just the set containing the numbers 1 through 6. These are the numbers that may show up when we roll a die. And then it's simple to say, okay, that's the sample space, but because of the condition that all throws came up even, this sample space gets restricted to just consisting of 2, 4, and 6. Now, there isn't anything inherently wrong with this, but it does make it really easy to make a mistake, and it will help us to take a more accurate view of our sample space. Really, we're asking a question about sequences of dice throws, and so our sample space isn't really consisting of the single possibilities of dice throws, but is rather consisting of the sequences of dice throws that end in a 6. Really, we should imagine our sample space containing things like this: sequences of dice throws ending in 6. 1, 1, 2, 3, 6, 4, 1, 6, and so on. And of course, there are many, many other possibilities. When we impose the condition that all of the throws have to be even numbers, many of these possibilities are eliminated, so the sample space is restricted. This is no longer under consideration, neither is this, neither is this. They all have odd numbers in them. We're being pretty picky here about the sequences we're considering. They have to be all evens, and they have to end at the first 6. There can't be a 6 anywhere else. The 6 has to be at the end. Now that we have what's really a more accurate view of our sample space as consisting of sequences of dice throws, let's get a little bit more general and consider sequences that end when something other than 2 or 4 comes up. So these are like the special sequences we were considering, except instead of ending when 6 comes up, they end whenever 1, 3, 5, or 6 come up. Here are a few examples of sequences like that. It's all 2s and 4s, but they end whenever a different number is encountered. 2, 4, 1, so it stops. 2, 3, so it stops. 4, 4, 4, 2, 6, so it stops. Now, let me ask you, how long are these sequences on average? How many throws would I expect it to take before something other than 2 or 4 comes up? Well, there are 6 sides on the die that are all equally likely to come up, and only 2 of them are 2 or 4. That means every time we roll the die, there is a 2/3 chance that the sequence is going to stop, because there's a 2/3 chance we're going to roll a 1, 3, 5, or 6. Now remember the reasoning we discussed before, thinking about sequences of even rolls that end with the first 6. We said, well, 1/3 of the rolls are 6, so we would expect it to take on average 1 divided by a third, or 3 rolls. Of course, that gave us a wrong answer. There is an error in this reasoning that we'll come back to, but that same reasoning is totally valid here. It is the case that there's a 2/3 chance each roll comes up 1, 3, 5, or 6 and ends the sequence. So the expected number of rolls is 1 divided by 2/3, which of course is 3/2, or 1.5. Now, I've already said that 1.5 is the correct answer to the original question. We've just established that it's the correct answer to this related question. Now we just have to connect them. Remember, our question here concerned sequences of dice throws that were all 2s or 4s, ending whenever a different number, other than 2 or 4, showed up. Now, the original question was just like that, except requiring that final number to be 6. Since it says all the throws have to be even, that's just like saying it has to be 2s and 4s until the end, which has to be a 6. Then the key insight is that you have to realize all of these sequences that happen to end in 1, all of these sequences that happen to end in 3, all of these sequences that happen to end in 5, And indeed, all of these sequences that happen to end in 6 are of the same kind, so to speak. Requiring them to end in a particular number, like 6, does not change their expected length. As far as the die is concerned, none of these numbers are meaningfully different from any of the others. Ending in a 6, there's nothing that makes that significantly different from ending in a 5. Certainly, requiring these sequences to end in a 6 is not going to change how long I would expect them to last. 6, 5, 3, and 1, those are all just individual sides of the die. There's nothing that makes any one of those numbers special, and requiring these sequences to end in a particular one of those numbers is not going to suddenly increase its expected length. Like, oh, the 6 is a very special breed. If we require the sequence to end in a 6, well, the sequences are going to go on way longer then. No, that's not how it works. I see it most clearly as a kind of symmetry. For every one of these sequences that ends in a 1, there's an equivalent sequence that ends in a 3, 2, 4, 3, and one that ends in a 5, 2, 4, 5, and one that ends in a 6, 2, 4, 6. Thus, whether we require them to end in a 1, or in a 3, or in a 5, or in a 6, or in just any of those 4 numbers, their expected length is still going to be 1.5. Before we do a more rigorous calculation, we can put this argument a little more formally in the language of random variables. Let's say we let n be the number of times you roll only 2s or 4s until you roll any other number. So in this example, n would equal 3. It took 3 rolls of 2s and 4s to get something else. In this example, n would be 2. In this example, n would be 5. Again, the last roll just has to be something other than 2 or 4. We're going to name that as well. We'll say let x be the die number on the last roll, so it's either a 1, a 3, a 5, or 6. Then, the argument we just laid out is that the expected value of n, the average length of these sequences, is the same as the expected value of n given a particular value of x. And this is the notation that represents that. If I'm only considering sequences that end in a 3, for example, so x is given as 3, well, it's no harder or easier to roll a 3 than it is to roll a 6, a 5, or a 1, so the expected value would still be 1.5. Of course, the same holds for the case where x is 6, which is our original question. Hopefully you're pretty convinced by now, but you may still be wondering what the error could have been with the original argument, which got an answer of 3 rolls. It is valid to consider this as a sample space with individual dice rolls, where the only 3 possible rolls are 2, 4, and 6, and then it's a geometric random variable that we're trying to find the expected value of. The problem is, after imposing the condition that all of the throws need to be even, which is how we got this sample space of 2, 4, and 6, we need to update the probabilities accordingly, and it's really easy to ignore that detail. While 2, 4, and 6 are all equally likely to come up when we roll a die, after imposing this condition that all the throws gave even numbers, and knowing that we end with a 6, these 3 die rolls are not equally likely anymore. In this situation, the actual probability of 2 is 1/6. The probability of 4 is also 1/6, and the probability of 6 is 2/3. Why is this? Well, consider all of the sequences of dice rolls, and specifically the ones that we are considering. We might roll a 2, and then a 4. But then if we roll a 5, these rolls are totally excluded. This sequence is not considered anymore. So then there are 2s and 4s that happened, but aren't under consideration. But this exclusion never happens to 6, because 6 is the end condition here. I could roll as many 2s and 4s as I like in a sequence, but if an odd number comes up before a 6, this sequence is thrown out. The only time a sequence of 2s and or 4s gets to be included in our space is if there's a 6 at the end. Each time I throw a die, it's more likely than not that I'm going to get something other than 2 or 4, in which case the sequence is either going to be excluded, or if I happen to roll a 6, then the sequence will be included along with that 6, of course. So that's why we have to update these probabilities appropriately so that we can treat this like a geometric variable with p equal to 2/3 and get a correct answer. We would say the expected value is 1 divided by 2/3, the ending condition probability of getting that 6, and of course 1 divided by 2/3 would give us 1.5. We're going to finish quickly with a more formal calculation of the expected value. The definition of expected value, which is what this question is all about, is the probability-weighted sum of the outcomes. So, regarding n as the length of our dice roll sequences, the expected value of n is the sum of a possible value of n multiplied by the probability that it takes on that value, and add this product up for all possible values of n, from 1 to infinity. The length of a sequence could be 1, or 2, or 3, or anything all the way up to any arbitrarily large number. Now, there are two ways you can view this calculation we're about to do. You can accept what I said about updating the probabilities of 2, 4, and 6, so that the probability of 6 is 2/3, and what we're calculating is the expected value of n, which is the length of a sequence of dice throws, where every throw is even, and it ends when a 6 comes up. That, of course, is exactly what the original question was about. Alternatively, you can view n as the number of times we roll only 2s or 4s until any other number comes up. We previously discussed why the answer to the expected value of this is actually the same as the expected value of the original question. As we do this calculation, I'm going to speak of n in these terms, so that this is what n is. And remember, I already told you that the expected value of a geometric random variable is 1 divided by that probability parameter, which in our case is actually 2/3. But now what we're doing is the calculation that would actually show that, in this case, from the definition. Now, the most important thing we need to use this definition is the probability that our random variable n would take on any particular value. The probability that a dice sequence is 2 throws, or 3 throws, or 4 throws. Thankfully, that's pretty easy to figure out. The probability that a sequence has a particular length n, well, all of the throws except the last throw have to be either 2 or 4. So that's 2 of the 6 possibilities on a die. That's a 1/3 probability, but let's just write it as 2 over 6. Now, if the total length of the sequence is n, there are n-1 throws before the last one. That means we need a 2 or 4 to come up n-1 times. So we have 2 over 6 to the power of n-1. Just like if I wanted a heads to come up 5 times in flipping a coin, the probability of that would be 1/2 to the power of 5. Now, if indeed the sequence had length n, that last nth roll must have been something other than a 2 or a 4, and there is a 4 over 6 chance of that happening, so then we would just have to multiply by 4 over 6, the probability of that last throw being something other than 2 or 4. Now that we've got this, which is called the probability density function, we can proceed with the expected value calculation. By definition of expected value, the expected value of n is going to be the sum of the probability that it takes on a particular value times that particular value for all the possible values from 1 to infinity. Note that I've reduced the fractions. 2/6 is 1/3, 4/6 is 2/3. And remember, we're multiplying by n because that is the particular outcome, and we have to weight each outcome by its probability and then add these all up. This is an infinite sum, or what's called a series, and just like in a normal sum, we could take common factors out. Every single term in this sum has a factor of 2/3, so let's take that 2/3 out. So we have 2/3 multiplied by the series. I've put that factor of n first just because that's my preference. Now, adding up an infinite number of things is not particularly easy, but that's where calculus comes in, and calculus students may recognize this as a familiar derivative form. Calculus students may remember this fact, that when the absolute value of x is less than 1, the function 1 over 1 minus x is equal to this, what's called a power series. It's a sum of powers of the variable x, from x to the power of 0, all the way up through x to the power of arbitrarily large numbers. So this is a way of expressing a function as an infinite sum. And of course, in calculus, there is this thing called the derivative, and the derivative of this function, which we write as f prime of x, can be found by taking the derivative of every term of this series, which gives us I times x to the I minus 1, just using the power rule. The derivative of 1 over 1 minus x, of course, is 1 over 1 minus x squared. And does this look familiar? Well, yes, it does. I times a variable to the I minus 1. Look what we have here. We have n times 1/3 to the n minus 1. For these equations to hold, the absolute value of x has to be less than 1. And of course, in this case, we have exactly this form, and what's playing the role of x does indeed have an absolute value less than 1, because of course it's 1/3. In other words, the value of this infinite series is, in fact, this function, but with x equal to 1/3. Then finally, that means we can write that this equals 2/3 multiplied by f prime, which is that, evaluated at 1/3, so times f prime of 1/3. And then we just have to evaluate this. So we have 2/3 multiplied by, this is f prime, we just have to plug in 1/3 for x, so we have 1 over 1 minus 1/3, that's 2/3, so this is 2/3 squared. Then we have a 2/3 out here. We have two factors of 2/3 down here, so one of them will cancel out, and there will still be one factor of 2/3 left in the denominator, and so this is 1 over 2/3, which of course is 3 over 2, or finally 1.5. And so that is the expected value. If we throw a die until we get a 6, the expected number of throws, conditioned on the event that all throws gave even numbers, is 1.5. It's not 3, and hopefully you are now convinced. Again, I said that I was considering this final calculation with n being the number of times we roll only 2s or 4s until we roll any other number, but I think it's easy to see that that does not change if we fix that final number to be something in particular, like 6. So that's the problem, the common error, and the solution. Let me know what you thought down in the comments, and if you have any questions, please do let me know. If you enjoyed this video, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to all sorts of rad videos. And finally, be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the table. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.
Planet faded.
Sun